we were trying to prove the equivalence of various forms of spectral theorem, resolution of identity, L infinity continuous functional calculus, L infinity functional calculus and the multiplication operator form, right. So, these 4 equivalences. So, we had done 3 of that. So, what is remaining is that the L infinity functional calculus implies a resolution of identity, right. So, that is the 4th one. Okay. L infinity functional calculus implies resolution of identity. Okay. So, we need to construct a resolution of identity for our operator, right, resolution of identity. Okay. So, so L infinity functional calculus we already have, right. So, we have phi of A. Okay. So, let us call it phi sub A just to denote the dependence on phi dependence on the operator A, or sometimes we will simply write phi. Okay. So, when there is no. So, what is phi of A? So, phi of A from L infinity of minus norm A to norm A to bounded operators on the Hilbert space H, right, separable Hilbert space. It has all the properties we want, right. So, it is a star homomorphism continuous and identity function goes to the operator A, right. So, that is something one should keep in mind, the identity function. So, that is I d x equal to x, x going to x is the operator A. Okay. And it is a star homomorphism. So, product of functions will go to product of operators. It is continuous, which means that the norm of phi g will be less than or equal to the L infinity norm of g. Okay. Now, we want to define the resolution of identity, right, using whatever is existing, the functional calculus, L infinity functional. So, let chi t of x be equal to 1 if x is less than or equal to t, right, 0 if x is greater than t, right. So, this is the indicator function of minus infinity to t, right, and then we look at the corresponding operator. This is a bounded function, right. So, chi t is a bounded function, it is an L infinity function. So, I can look at phi of chi t, right, I will get an operator. So, define E sub t. So, that is the resolution of identity I want to define, E sub t equal to phi A, that is the homomorphism we have which defines the L infinity functional calculus of this bounded function chi sub t. Okay. Then then you have to prove that it is a resolution of identity, that is more or less straightforward, but at least let us see some properties. Then clearly E sub t are projections, right. Why is that? Because chi t is equal to chi t bar equal to chi t square, right, implies E sub t which is phi A chi t equal to E sub t star which is phi A chi t bar equal to chi t square has to go to E t square, right. So, these are all self adjoint projections, there is no problem. And what are the other properties? You need to check that right continuity of E sub t, and as t goes to minus infinity I want it to go to 0, as t goes to plus infinity I want to go to 1, right. These things are more or less clear, because if t goes to minus infinity chi t will go to 0, right, pointwise and bounded, right, it is going to 0 pointwise of course for any x, chi t if t goes to minus infinity after some time chi t will be 0 and everything is bounded by 1, right, mod chi t is less than or equal to 1. for every t. So, it is pointwise and bounded, and because of the L infinity functional calculus I know that phi a chi t, right, but this is nothing but E sub t will go to 0 in the strong operator topology. Strong operator topology, right. So, this goes to 0 in the strong operator topology, and that is precisely the condition, right, that t going to minus infinity to should go to 0. Similarly, t going to plus infinity E sub t goes to the identity operator, right, because chi sub t goes to the constant function 1 and the constant function 1 goes to identity operator. But this is happening in the strong operator topology because the convergence is in the convergence is pointwise and bounded. Okay. So, similar, so I will leave the similarly this and the right continuity. Okay. Right continuity of E sub t. Okay. So, all that follows exactly like this using the pointwise and bounded bounded convergence of chi sub, let us say T n to chi sub t. Okay. So, recall that, well, so this does not finish what we want, because we wanted a resolution of identity, right, and the resolution of identity should be such that the operator A is obtained by integrating the identity function, that is t going to t with respect to E sub t. So, let us justify that. Okay. So, recall that. So, once you have the resolution of identity, so that we already have E sub t, then whatever we did in the beginning after defining the resolution of identity, we defined all this phi n g and then took the limit and proved that it existed, we got phi g, which was the L infinity functional calculus, right. So, we can sort of go back. So, if I look at phi n g, well, what was this? This is equal to minus 2 to the n norm A to 2 to the n norm A, right, j equal to. So, g of j by 2 to the n, remember these expressions, E at j by 2 to the n minus E at the other end point j minus 1 by 2 to the n, right. This was the expression for phi n g. Then phi n g converges to phi of g in the operator norm, right, in the operator norm. Okay. So, this is why I should have said phi sub a. So, phi sub a is the L infinity functional calculus coming from the operator A. Using that L infinity functional calculus, we defined the resolution of identity E sub t, right, and using the resolution of identity we can define these phi n's, and once we have the resolution of identity we know that these phi n's will converge to something which we called phi. Okay. We need to say that phi and phi sub a are same, okay, but that is not difficult. So, this converges in the operator norm for at least continuous functions, for g continuous, right. So, if g of x equal to x, so I want to know what happens to this when the identity. So, okay, so phi g it converges to phi g in the operator norm for g is continuous, and we denoted by phi g the integral g det, right. Now, our aim is to show that when g is the identity function, that is g x equal to x, I am going to get the operator a which I started with, right. So, g x equal to x, then phi n g is equal to, I will write down this and explain, phi a of q sub n. So, there are two things here, phi n g is what we have defined here using the resolution of identity, right, this guy. Phi sub a is the L infinity functional calculus given to us. Okay. So, that is a given homomorphism. I am saying the expression of phi n g is same as phi a of q n, where q n is a bounded function. So, let me write down this, where q n is a bounded function such that mod q n is less than or equal to norm A. Okay. And q n x converges to the function x pointwise and bounded. Okay. So, why is that? Well, this it is writing down, this can be quite messy. So, you can use the multiplication form if you like, or any other form which we have proved before to see this, at least that will justify it. So, essentially you write phi n g, which is this expression, as phi a of q n. So, q n is going to be a step function, right, which essentially connects the values of g, and that expression will be equal to phi n g, and this expression. So, you have to sort of picturize this. So, you are looking at g x equal to x, right. So, that is j by 2 to the n. So, I have all these j by 2 to the n. So, think of certain step function there, and these step functions as n goes to infinity, these intervals become smaller and smaller, and you will finally get the function x. So, that is why these q n's will converge to x pointwise and bounded. Okay. So, there is some justification to be done there. So, but I will leave it to you, such that q n x converges to x pointwise and bounded. And so, but I know that phi n g converges to phi of g in the operator norm, and that is my g det, right. So, integral over x det will be phi a of the identity function, but that is a. Okay. So, yeah, maybe I should write t here instead of x. Okay. So, this was the one which was missing from there. Okay. So, all these forms are equivalent, all the resolution of identity, multiplication form, the L infinity or the continuous functional calculus, they are all equivalent. And if I take a normal operator, we have already proved the continuous functional calculus, which was simply the Gelfand-Neumark theorem, right. So, all these forms are true for any let us say self-adjoint operator, because here we restricted it to self-adjoint operators. So, we can use any of them now. So, let us continue. A be a bounded self-adjoint operator. The following sets are same. So, this is going to be a description of the spectrum of A in various terms. The following sets are same. Okay. 1 sigma of A. So, that is the usual spectrum of A, right. Spectrum of A, right, all those lambda such that A minus lambda inverse is not bounded, or inverse does not exist. 2. Now, given the self-adjoint operator, we have a unique resolution of identity, right. So, the set of points of increase of E sub t. That means, wherever the E sub t is sort of jumping, right, E sub t, the resolution of identity, of A, right. That is, so E sub t is the resolution of identity of A, and the sets of points of increase of E t, meaning wherever it jumps. So, that is all those t such that for every epsilon positive, E t minus epsilon is not equal to E t plus epsilon. Okay. So, for every epsilon, right. So, there is a jump at that point t, right, that is what it means. So, remember these are all increasing projections, right, increasing in the sense if t is less than s, E t is less than or equal to E s in the sense of positive operators, right. So, if they are equal, that means in that particular interval there is no mass for E sub t, right. So, it does not increase, but the spectrum is precisely where it jumps. Think of the finite dimensional case, maybe this will be much clearer there. The support of spectral measure for A, okay, that is. So, I did not define what a spectral measure is, but this is simply the measures that appear in the multiplication form for A. So, remember A can be realized as multiplication by x on some L2 space, right, or a direct sum of L2 space with respect to certain measures, right. So, that is, so let me write down that is you look at union support of all those mu j over j and take the closure. Okay. So, what does this mean? If you recall the multiplication form, so in the multiplication form, the Hilbert space H is direct sum of L2 of, well, instead of R you may have the minus norm A to plus norm A and so on, but you had something like this, right. So, you had those measures mu j, does not matter what form you take, meaning what cyclic vectors you start with, you have this mu j's, okay. It does not matter which order you take those cyclic vectors and all that. These mu j's, once you have those mu j's, the support of those mu j's and you take the union and the closure, that will give me the spectrum, okay. So, and A is identified with multiplication by x, right, multiplication by x, right, all right. So, let us prove this. So, 3 statements: the spectrum, the jump of the resolution of identity. So, if you look at the finite dimensional case, you will see this immediately, right, because you have finitely many eigenvalues, and if you look at the resolution of identity starting from minus infinity, it is 0 until you hit the first eigenvalue, right. At the first eigenvalue you get the projection to that particular eigenspace, and then it does not increase until the next eigenvalue. Once it comes to the next eigenvalue, you have the projection to that plus the projection to the previous eigenvalue, right, that would be your E sub t there. So, at each eigenvalue there is an addition of the projection, right. So, the resolution of identity jumps, and that is precisely the spectrum, right. So, wherever it jumps is the eigenvalue in the finite dimensional case, and in the infinite dimensional case that will correspond to the spectrum. So, jumping cannot be written in precise form when you have this spectrum to be an interval and so on. So, that is why this particular form is there. Okay. For every epsilon positive, if you go below t, that will be that projection will not be equal to E t plus epsilon, right. So, essentially at t there is some growth or some jump. Okay. So, let us prove this. First we will prove the containment of 1 in 2, right. So, or 1 in 3, yeah. So, first we will show that sigma of A, so that is the spectrum of A, is contained in the support of the measures of the spectral measures, right. So, support of mu j, j bar. Okay. Okay, so let us do that. So, we will show that the complement of the right hand side is contained in the complement of the left hand side, right, that is enough. So, let lambda naught be not in the support of these spectral meshes. Okay. Now, recall that A can be realized as a multiplication by x on this L2 space, right. So, that is important, recall that A can be realized as multiplication by x on L2 of, well, I will write R or minus norm A to norm A, right, the measures are going to be supported there anyway, d mu j direct sum j equal to 1 to let us say capital N. Capital N could be finite or infinite. Okay. So, finite or infinite. Now, I am taking a lambda naught which is outside, right. So, yeah, maybe some picture is good. So, I look at some lambda naught which is outside the support of mu j's, right. So, let us say support of mu j's is here. This is the support of mu j's over j, you take the closure, okay, that interval, and lambda naught is away. Clearly, the function, so I want to say it is not in the spectrum, okay, the function. So, it is multiplication by x, right, the operator is multiplication by x, and I want to say lambda naught is not in the spectrum. What should I do? I should be able to invert x minus lambda naught, right, x because multiplication by x minus lambda naught, right. A is multiplication by x. So, A minus lambda naught times identity will be x minus multiplication by x minus lambda naught. So, clearly the function g of x equal to, so I am going to define it to be 1 by x minus lambda naught. So, 1 by x minus lambda naught of course is not a bounded function on the real line, I have to make it bounded, but remember lambda naught is away from the support of all the measures. So, on the set where the mu j's survive, right, 1 by x minus lambda naught is bounded. Near lambda naught I can define it to be anything, right. So, I will define it to be, so let us say I choose, so let us say this distance is d and up to here I have the distance d by 2. Okay. So, I will define this to be x minus lambda naught if mod of x minus lambda naught is greater than or equal to d by 2. Okay. So, d by 2 is this much distance. So, if it is here, right, or I can go up to here also lambda naught plus d by 2 on this side, also it is 1 by x minus lambda naught, but that is a bounded function. Near lambda naught, that is in a neighborhood of lambda naught, I define it to be something 2 by d, it becomes actually continuous, does not really matter. Okay. If mod of x minus, I mean it has to be a measurable bounded function, that is all I need, okay, less than d by 2. Okay. So, now if you look at what is happening in the support of mu j's and the closure, the function is just 1 by x minus lambda naught, there is no problem, and it is a bounded function, right. So, I have inverted the multiplication by x minus lambda naught in that in the union of support of mu j's, right, and that is enough. So, it is invertible. So, lambda naught cannot be in the spectrum. Okay. So, the function is bounded, g x is and measurable, and is the inverse of a minus lambda naught I, right. So, this implies that lambda naught is not in the spectrum of A, right. Okay. So, let me explain that a little bit more, because I have A to be multiplication by x, right. So, A minus lambda naught identity is I am looking at m x minus lambda naught times identity, right. This is nothing but multiplication by x minus the function x minus lambda naught. I want to say it is invertible, right. To say that it is invertible, to say that multiplication by x minus lambda naught is invertible. So, invertible in some L2 space, let us forget about the direct sum and all that, let us say L2 of some nu, right, on the real line or minus a to a or something like that, or let us say L2 of some interval, okay, and some measure, some finite measure nu, okay. So, finite measure, because then you apply it to the direct sum, right. So, to say that multiplication by x minus lambda naught is invertible, well, if it is invertible, it is multiplication by x 1 by x minus lambda naught, right, is equivalent to saying that the function 1 by x minus lambda naught is in L infinity of nu, right. We are looking at support of mu j and then union j and right, and lambda naught is outside that, right. So, lambda naught, the point is outside that. So, if this is contained in some interval, let us say this is my a b, 1 by x minus lambda naught is somewhere here. So, 1 by x minus lambda naught there will be bounded, and so I can apply whatever I have just said now, which is a trivial statement, that 1 by x minus lambda naught is actually in L infinity of these measures, okay. And so it is invertible, right, and so lambda naught cannot be in the spectrum of A. So, now since we have done this for one, you can do it for all the direct sum, right. So, it is invertible at each level, right. I have direct sum j equal to 1 to n L2 of R d mu j, and if lambda naught is outside the spectrum of all the mu j's, 1 by x minus lambda naught will be in the L infinity for all the mu j's, which means that a minus lambda naught, which is identified with multiplication by x minus lambda naught, is invertible, right, at each of this direct sum, which is same as saying that lambda naught is not in the spectrum, okay. So, now well perhaps it is a good time to stop. So, we will prove that we will prove the other two equivalences. So, as of now we have only proved a part of what we want to say. The support of the spectrum is contained in the support of these spectral measures. The equality is what is more important, that the support of all the spectral measures together will give me the spectrum, okay, and the spectrum is also equal to the jump of this resolution of identity. So, the remaining two parts we will prove in the next class, okay. So, we will stop.